Good afternoon. My name is John Coonrod. I'm with Rogers Corporation, and I'm going to talk to you today about a new software that we have brought to our technology hub for download. It's a free download. And if you haven't been to our technology hub, I'll give you a quick rundown of what's there. On our technology hub, we have a lot of articles that pertain to circuit design and microwave, millimeter wave. We have articles and white papers for material characterization, for circuit fabrication, variety of things like that. We also have several tools on our technology hub that could be of interest. Some of these tools are converters, and some do impedance modeling, loss modeling, things like that. The most recent addition to the technology hub is this software. And it does, as the name implies, it basically determines the dielectric constant of a material when evaluating microstrip transmission line circuits by phase response. So that's what I'm going to talk about today. And the agenda I plan on going through shown here. I'm going to talk about the microstrip differential phase length method. Not getting in a lot of detail there, but just kind of give you a good overview of what the method is, what it entails. And then also the procedure of testing the circuits and what goes on there. And then finally, I'll give you some examples with screenshots of the software itself, and kind of walk through that and let you understand how that works. So to begin with, the microstrip differential phase length method, this is not a new methodology. It's been around for a number of years or even decades. And really what it is, just breaking it down in simple form, is you're testing two circuits that are as identical as you can make them, and the only difference being the length, the physical length. And what you do is you build the circuits on the same sheet of material, and they will be in close proximity to each other, and you want to have them as identical as possible to each other. So they want to have the same circuit design, you want to have the same everything. And if you're going through a circuit fabrication process where you have copper plating, you want to make sure that the copper plating is consistent. So as much as possible, you want these circuits to be exactly the same except for the physical length. And the physical length needs to be a significantly different length, a shorter circuit and a longer circuit. The shorter circuit, longer circuit, usually a good ratio is 1 to 3. I typically use a 2-inch long circuit and a 6-inch long circuit. And there's some exceptions to that, but if you do violate that, you want to go on the high side, maybe a 2-inch versus 8-inch circuit or something like that. The shorter circuit's actually going to be the limiting factor when you look at the lower microwave frequency responses. I'm going to talk about that a little bit later on. The good way to test these circuits is really with a fixture, and there's a multiple of different kind of fixtures out there that could be used. And the reason why you want to use a fixture or something like that is because you're trying to make sure that besides these circuits being exactly the same except length, that also the signal launch is exactly the same. So some of these fixtures, some are made by Intercontinental and others, but it's basically a clamping mechanism where you have a signal pin and a ground plate below there. You put your circuit in, sandwich it together. The ground plate is picked up by the pressure plate that's holding it in place. So the pin touches the signal on top, and you've made connection to your circuit. The nice thing about that is you have kind of the same signal launch on each circuit that you test. And that's what you want to have. So you want to have everything identical as possible except for, again, the physical length. So you want to have the same signal launch. There's also, of course, probe stations. You can use probe stations. That'd be a good idea. I actually use a lot of the in-launch connectors that are the field serviceable type that are not soldering. So you can put these connectors on the circuit and use the exact same connectors for the other circuit. The reason I use some of those in-launch connectors is because you get a lot of different models, and these different models can help you on getting a better signal launch for different constructions. So a thicker circuit may have a different need than a thinner circuit for signal launch, and you have these different connectors that you can pick from to get a better response that way. The test method here, the differential phase length method, is really a transmission reflection technique. And there's a lot of different test methods out there to characterize microwave materials. And most of these test methods are generally resonator type test methods or perturbation resonators, something like that. The reason that we were interested in this particular test method, being a transmission reflection technique, is that you really can get out of it a decay versus frequency curve. So you can get a dielectric constant response over a wide frequency range. Whereas if you do this with a resonator type of test, the resonator is going to give you a dielectric constant or its properties at a particular frequency or maybe harmonics of that. But this type of test is going to give you a dielectric constant over a wide range of frequencies. More specifically, being that it is a microstrip transmission line, you're really going to be looking at the phase response of the wave mode, which is a quasi-TEM wave. And the formulas that are used in the software are given here. And there's more to it than this, but that's kind of the basic idea. The first formula on the left there is the microstrip phase response formula. And phi to the left there is the phase angle, and that's equal to, as you can see, a variety of things. One of them, L, is the length. That's the physical length of the circuit, C is the speed of light. F is the frequency you're testing at, and then the effective epsilon sub r is the effective dielectric constant of the microstrip. So that's for a particular one microstrip circuit. Now when you have two microstrip circuits like what we're doing and having a different length, then you alter that formula to the center formula. And now what you have is a difference in length, the delta L. That's the difference in length of the circuits that are being tested. And what you're going to measure is the phase response of that, which is going to be the delta phi. And that, again, is going to be the phase response at a given frequency. And then rearranging that formula to get the effective dielectric constant. Once you have the effective dielectric constant, then you can use EM software if you'd like. And in some cases, we may read this effective dielectric constant, excuse me, we might read this number into a field solving software such as Sonnet, which I've used before. It works very good. And in this case, this particular software will use the effective dielectric constant, and then it has its own routine to solve for the dielectric constant of the material itself. And the routine that it's using is actually from a paper that was from many years ago for Hammerstedt and Jensen. And it's a really good paper on calculation of impedance and losses for microstrip transmission lines. Also, for a reference for this test method, if you'd like a little bit more information on it, the bottom here is a paper written by Das, Posar, and Voda. And this is a really good paper to talk about the same test method. It gives you a lot more engineering rigor than what I just went through real quick. But the reason I like this paper is because it's also pretty practical too. It also gives you some examples, and it also gives you some accuracy issues and how to deal with them. So I went through the idea of this pretty quick, and if you want some more details, that's a pretty good reference. So the procedure for doing the testing is, again, to make these circuits that are, the biggest difference is the physical length, everything else being the same, the signal launch pretty much the same as you can make it, and then using a network analyzer to measure the unwrapped phase on S21. And what I typically do is set up here for the network analyzer I use is a PNA that's capable of 10 megahertz to 50 gigahertz. And the settings I found to be most useful for this type of test I've given here, where it's 5,000 points, 1,000 hertz IF bandwidth, and then you do want to save the format in a file. You want to save the file in a format of S21 unwrapped phase. So once you have the circuits measured, and again, everything being the same except for the physical length, now you need to get the software, obviously. So you go to our Rogers Technology Support Hub website, download the software, and this is the link for that download. As part of the download, you can also download the user manual, which I'd highly recommend. The user manual tells you how to install the software, which is pretty simple, but also gives you examples about how to use the software. It gives you a lot more details of the theory behind the microstrip differential phase length, and it also gives you a lot more of the more examples of exactly how the software works. This is a screenshot of the software. And I've tried to make it pretty simple, so it's only got one screen on the entire software, everything on one page. And what you have is, after you've measured the circuits, you should measure a shorter circuit and a longer circuit, then you need to read in these files from the network analyzer. And the files, I usually give them a name that's meaningful. And you can see in the upper left is the shorter file, and I've given it a name of 2-inch long, and it's a 2-inch transmission line using R3003 materials. And the 5RLD is just a type of copper. But anyway, the file name should be descriptive, so it kind of gives you a reminder of exactly what you're doing. If you do enough of these tests, it can get a little confusing, so it's always good to have a file name that's pretty descriptive. So this is the shorter file that you're going to read in, the data from the network analyzer. And then this next window would be the file for the longer circuit. So you'll read these in, and then you can define what the output file is going to be. The output file can be whatever you want it to be for name, but it's going to save as a TXT file, and it's going to be more specifically a comma delimited file that can be read into Excel. And then you can take that data in Excel and make your own charts or manipulate the data, do what you will with it. So as part of this page, there's other things you can do too. So by default, it says you're going to be bringing in the data as the incoming data is unwrapped phase. And coming off the network analyzer, that's common, but it's also common to have unwrapped phase. I'm sorry, unwrapped phase is the thing that you should be bringing in. It's kind of common to have wrap phase coming off the network analyzer. So if that's the case and you save the file as a wrap phase, then you can click on the button there and it will convert it to unwrap phase, which is exactly what the software uses. Now there's also another thing you can do, and that is you can save this information of the shorter circuit and the longer circuit as a group delay. And group delay can also calculate the dielectric constant over frequency, but I've tried to refine the software as much as I can, and there's still more noise in the group delay measurements than the phase. And I've come to the conclusion it's just kind of the nature of the beast. I can't say that I understand it real well, but just from what I see, it seems like the group delay typically has a little bit more noise than the phase response. So by default, I usually have the incoming data as unwrapped phase on S21. And then also you can determine the range of calculations. Normally by default, it's going to give you the range that it reads in off the files. And you can determine other ranges if you'd like. So you can tell it to calculate a defined range of points, maybe 1,000 points to 2,000 points, or you could actually determine a frequency. So you could look at only the dielectric calculation for the dielectric constant from 16 gigahertz to 18 gigahertz if you'd like. So you can select all that here, and then after that, you need to put in the circuit parameters, which are up here, and you also need to give it an approximate dielectric constant. So this is kind of your guess of what you think the dielectric constant of the material is. And right now I have this as a 2 decimal place, and normally I don't do that. Normally 1 decimal place is fine, and in some cases I'll even put a whole number in. But what happens is the less accurate your approximate decay is the longer the program runs, basically. So it's doing a convergence routine, and the closer your approximation is, the faster the program gets there. It does not really have much effect on the accuracy of the results as much as just the speed. And in this case, this software takes usually, depending on the speed of the computer, anywhere from 7 to 12 seconds to run. And if this approximation is very far off, it might get up to 20 seconds. So it's not a huge amount of time. The one drawback would be is if you put in for the approximate dielectric constant a number like 9, in reality it's about 3, then that's going to probably cause a problem. So you want to be kind of close. If you are that far off, then it will give you an error and telling you you're pretty far off and you need to fine tune it. And a lot of times it'll give you an approximate number that you should use. It's a little more appropriate. Then the measurements of the circuit itself, these are pretty important. So the circuits that you're testing, the short and the long circuit, you need to give this program what is the conductor width, what's the copper thickness, what's the substrate thickness. Now on a thicker circuit that's 30 mils thick or thicker, then these dimensions are a little less critical. They're still very important, but when you get down to the thinner circuits, that's when these dimensions get really important. And if the circuit is about 10 mils thick or thinner, then these dimensions become extremely critical. So a lot of times I'll do a microsection to get the exact substrate thickness and the copper thickness and the conductor width. Along with that, you put in the difference of the length of the 2 circuits. In this case, I actually got the wrong number in there. The circuits I read in is a 2-inch circuit and an 8-inch long circuit, so the difference obviously should be 6 and not 4. But nonetheless, and then the output file is generally raw data, and I'll show you that in a second, but you can actually have an average decay. And what the average decay file pretty much tells you is the dielectric constant at integers of gigahertz. So maybe an average dielectric constant at 1 gigahertz, 2 gigahertz, 3. Generally speaking, though, I just leave it with the raw decay data. So once you have all that done, you hit the convert button, and initially what you get is a table of information. Table of information has a scroll bar on the right, and you can scroll through the information, and it's based on frequency, so you can go through different frequency and look at the effective dielectric constant and the dielectric constant at those frequencies. And then as the program runs too, it also generates its own file, an output file. And the output file, like I said before, is a text file that is comma delimited that can be read into Excel. And that's the file that you've named here, and it's also going to be in the folder you've defined. And as part of this also, you can click on the tab for the looking at the data as a chart, which I've done here. And you can see the chart as frequency dependent, so across frequency range is showing you the dielectric constant. You can press on the setup button, of course, and change the parameters, so you can change the scale and things like that. And one thing I wanted to mention, though, a comment that I made earlier, was that the shorter circuit of the set of circuits, the short and the long circuit, the shorter circuit has more effect on the accuracy of the lower frequency measurements. And what that means is, in the low frequency range, there's something that happens that basically the shorter circuit is not going to act like a transmission line at certain frequencies. So the rule of thumb is that the circuit has to be a quarter wavelength or more to act like a transmission line. And what happens is a 2-inch long circuit, when you get down on low enough frequencies, it's no longer behaving like a microstrip transmission line, and now the mathematics pretty much blows up. And what you get is these dielectric constant numbers that go up into the hundreds of thousands, and that's just because the shorter circuit is no longer acting like a transmission line. So if you really want to look at microwave at lower frequencies, the shorter circuit probably shouldn't be a 2-inch circuit. You might want to try some other things like a 4-inch circuit and 6-inch or something longer. That gives you a little better response, a little better resolution down at the lower frequencies. The other thing about this chart is the nonlinear area down at the lower frequency range. That's actually legitimate, and that's not due to this wavelength thing that I've been talking about. That's actually due to the nature of any circuit material, and that has to do with moments of relaxation. And there is something that the material scientists know pretty well, and that's a phenomenon that happens with materials, that the dielectric constant versus frequency becomes nonlinear in a certain area, and that really has to do with these moments of relaxations. And so this nonlinear area is actually valid, and it's true, it's there, it's shown. But the thing I was talking about earlier about the shorter circuit having less accuracy at lower frequencies really has to do with these numbers that are going up the y-axis and kind of blowing up because it's not acting like a transmission line. Anyway, that's really all I have, and I think I have a couple of minutes for questions still. I know I went through that pretty quick, but any questions, anything I can help with? Yes, sir. Right, yeah. Yeah, actually, that's a good question. On a real printed circuit board, this is not a good drawing of a real printed circuit board because you get more of a trapezoidal effect. It's not really a rectangle, it's more trapezoidal. And being that you have a lot of electric fields between the bottom of that signal conductor and the top of the ground plane, I usually measure the widest part of that trapezoidal width because that's where the concentration of electric fields are. Oh, I'm sorry. The thickness? Yeah, actually, I usually measure that right in the middle too. Yeah, right in the middle of the conductor, kind of like what I have shown there. Other questions? Yes, sir. I'm sorry. Oh. Right. Yeah, you're still calibrating out to the connectors, that's true. And the unwrap is just, if you look at normal response on a network analyzer, if you just look at the wrap phase, you usually go from minus 180 down to 180, minus 180. Anyway, I'm saying wrapped, whereas you're actually making accumulation of that, where you're adding it all up. Is that answer to you? Okay. Any other questions? Yes, sir. I'm sorry, I couldn't hear you. Oh, loss tangent? No, this software does dielectric constant only. Yeah. Yes, sir. I'm sorry, I couldn't hear you. Oh, yeah, that's another good question too. Yeah, the question was if we're going to be putting these curves on our data sheets. On the RO4000 data sheet, I believe we already have some of these curves, and we're talking about adding that to more of our data sheets. And there's pros and cons to all that, of course. The good side of that is you can look at a specific frequency and see what the dielectric constant is, but that's also for a microstrip transmission line only, and if somebody's designing a strip line or a coplanar, there could be some subtle differences. But I mean, this is really meant to be a good approximation of how the circuit's behaving. But yeah, we've already got that on our 4000 data sheets, if I'm not mistaken. Other questions?